And what I want to do first is pull out the handout here, some basic properties of radicals that we talked about some in the last chat. And the one things I wanted to look at here is toward the bottom of the handout. We're going to talk about simplifying radical expressions here. And what's going to help us do this is a few rules. One is called the product rule, which is if you have any radicals to any roots, let's say, for example, if you multiply square root times square root, you get square root. Cube root times cube root, you get cube root. Fourth root times fourth root, and so forth. You can take radicals, large radicals, and break them up into smaller ones. You can take fractional radicals, and you can break those up into smaller ones as well. So we're going to look at both what's called the product rule for radicals, which means multiplying them, and the quotient rule, which means dividing them, and see all the different things in section 7.3 and 7.4 we can do with. And if I've got time, I'll sneak in 7.5 here as well. So let's go ahead and let me clear the slide. And remember, these handouts can be found in course documents in Angel. So what I'm going to do first, starting out 7.3 topics, is we're just going to take a few real easy ones here and warm up. So we're going to take the square root of 5 times the square root of 2 and just multiply those together, which will give us the square root of 10. So square root times square root gives you square root. Let's try another one. The cube root of 4 times the cube root of 9 is the cube root of what? Yes, you guessed it, 27. And we could go on with this. When can it stop, Young? The fourth root of 4x cubed times the fourth root of 5 equals the fourth root of 20x cubed. So you can see if you just multiply what's underneath each radical, you will get the product of what's underneath, called the radicand from last week. All right, so there's a few involving the product rule. Now let's look at some examples involving the quotient rule here. So let's take, for example, the square root of 2/49. And that would equal the square root of 2 over the square root of 49. So again, you can take fractional radicals and you can break them up into smaller components. So this would simplify into the square root of 2. And of course, the square root of 49 simplifies into 7. All right, let's try one more of those. The cube root, and we'll take a fraction here, of 427 is the cube root of 4 over the cube root of 27. So that would give us the cube root of 4. And of course, the cube root of 27 is one of our friendly ones, and we get 3. Okay, so let me clear this off here. And we're going to talk next, and this is more of 7.3 topics here. We want to talk about what is called simplified radical form. Okay, so what we're going to do is we're going to take a few radicals here, and I'll start out again with an easier variety. Let's take the square root of 27, and we want to simplify it by breaking it apart to get all of these square root numbers out of there, all the perfect squares. Now, if you think about nice square root numbers, the square root of 4 is 2. The square root of 9 is 3. So these are all like perfect square numbers, and you know how I'm getting those. I mean, my lecture classes would say, well, you're the math teacher, that's why you're getting them. I'm just taking 2 squared, 3 squared, 4 squared, and those will give you those nice perfect square numbers. Okay, so the square root of 16 is 4, because really a square root undoes or takes out the square. All right. Now, do you see any nice square root numbers that we can use this product rule on 27, and it would be, well, the square root of 9 times the square root of 3 would give us the square root of 27 using the product rule. And it just so happens the square root of 9 is one of those what I call friendly radicals from last week, and we'll get the square root of 9 is 3 times the square root of 3. So that is how you would simplify this. So this right here, answer-wise, and I'll circle it in a nice pretty color here, I'll go blue on it, is simplified radical form. Alrighty, now let's go ahead and take some other numbers here, and I think I'll look for one of my handouts real quick here, and I want to go back to something we did last time, and I'll be right with you. It's coming up as we speak. Our friendly radicals. So notice I again, on this handout, again found in course document, the friendly square root numbers come from perfect squares. Friendly cube roots come from perfect cubes. 1 cube, 2 cube, 3 cube, 4 cube, so forth. Friendly fourths come from numbers raised to the 4th power, 1 to the 4th, 2 to the 4th, 3 to the 4th, and so forth. So these are the numbers when you're trying to simplify radicals that you're trying to go after. So try to familiarize yourself with those. Now, you don't have to memorize all of these. I mean, you can go and make a little list if you need to. As we do some examples, I'll show you what I mean, and we'll go from there. All right, so back to some more examples here. So what if we get something like the cube root of 108? And they ask us to write that in simplified radical form. All right, now most of you are pretty good with those square root numbers, but how are you with these cube root numbers? I took the handout away. You can't see them anymore. So to get nice perfect cube numbers, just come over here and watch how easy this is. We'll just go ahead. 1 cubed, 2 cubed, 3 cubed, 3 times 3 times 3, 4 cubed, and you see how quickly these numbers, how large these are getting? Now 5 cubed, see, once we get to it, and you can check these on your calculators, is beyond the number we're trying to simplify. So what we're looking for when we simplify a cube root, will one of these perfect cube numbers go in to 108? That is your question. And I do believe that 27 is the number. Let's check it out here. I'm saying if I use the product rule for radicals on this, I would get the cube root of 27 times the cube root of 4 would give us the cube root of 108. And it just so happens the cube root of 27 is 3. And if you don't believe me, check it on your calculator. Now, Young, how do I check the cube root of 27 on my calculator? And remember last week, if you looked at the other video, you would put in 3, excuse me, this x root number. And, you know, they might just have an x root with nothing in here. They might have something in here, but that's the key. And then you would put 27 in. And remember, the way to check that is the cube root of 27 is 3, because this answer 3 raised to that root number will always give you what's under there, the radicand. All right, now that we've looked at some numbers, let's look at some variables as far as simplifying. Now, variables are even easier. So let's look at the square root. Now, this is from last time as well. The square root of x squared is x, if you remember last week's lesson, because you have that E over R rule, which means exponent divided by the root number. Okay? Let's try some more. The cube root of y12 would be y4, exponent divided by root. The fifth root of C20 would be C4, which could be considered an explosive, but let's not go there. All right, so again, if you take exponent divided into root, this is what we had earlier. Now we're going to take that and build on it. Now, Young, what if someone gave me something like this? The cube root of y to the 11th power. Now, what I would have you to do is say that you'd have to simplify this by using the product rule. And what I would do is try to break it into the cube root of something y to some power times the cube root of y to some power, if I was showing this like I did with numbers there. And I think the best two powers to pick here would be the cube root of 9 times the cube root of y squared. So the cube root of y to the 9th times the cube root of y squared. Now the cube root of y to the 9th, see, comes out as y to the 3rd power, the old E over R rule, whereas the second radical is simplified because as long as these exponents under the radical are smaller than the root number, that's what makes it simplified. So this simplified answer would be y cubed times the cube root of y squared. So cube roots really eat up cubes. Now another way to think about this, and I'm trying to think of better ways to explain this every semester so students see it better, is if we took y to the 11th, we could do this. We could say y cubed, cube root of y cubed, times the cube root of y cubed times the cube root of y cubed times the cube root of y squared. See, that would also, when you multiply all of those same bases, you would get y to the 11th back. So what you would end up with is 1y coming out here, 1y. See, cube roots eat up cubes. So you're left with 3 y's and 2 left over. Or some students may just take this 3, divide it into 11, say it goes in there 3 times with 2 left over, and think about it that way. So maybe that's a good way to think about it as well. But whatever way you think about it, just make sure you feel good about it. All right, now let's do one with numbers and variables here. So I'm going to take the square root here, so we'll stay with those, of 64y to the 9th power, and they want us to simplify and write it in simplified radical form. Now again, using the product rule, and a lot of students won't break this one up, but I like to. I would say that's the square root of 64. Now that's a nice friendly square root, so we'll just leave it as is. Now what would you do to break y to the 9th up? Since it's a square root, I would say that it would best break up into the square root of y to the 8th times the square root of y. So if it's a square root, you want to try to keep saying multiples of 2 up until this point without going over. So 2, 4, 6, 8, and then you know that this is going to be simplified because this exponent 1 here is smaller than that root number. So when you simplify radicals, you're trying to get all of those squares out of there. Now we could write the square root of y to the 8th as y squared, y squared, y squared, y squared, but why? So here's our final answer, 8 square root of 64, square root of y8, y4 times the square root of y, again called simplified radical form. All righty, so I'm going to go ahead and keep going as far as I can, as long as I can here. Next, I want to try a cube root problem. Let's take the cube root of 40 y to the 10th power. Now, if I'm looking to simplify this, I could break it apart using the product rule into the square root of 40 times, I'm sorry, not the square root, what am I saying here? It's been a long day, sorry. The cube root of 40 times the cube root of y10. All right, now if I want to simplify the cube root of 40, let me come over here again and I'll just make a little list here of those nice friendly cube root numbers. And you already see that I found one. 2 cubed is 8, so that's going to be the thing that helps me break down 40. So I'm going to break down the cube root of 40 into the cube root of 8 times the cube root of 5. Now, the cube root of y to the 10th, and I think your software does it kind of funny. I mean, if I'm right here, I think in the Math Excel software, it kind of does it funky. I don't think I've ever seen anything like this, but what it does is it'll take the cube root of y10, and if I'm not mistaken, it'll write those y's actually, I think it'll just write all 10 y's out here, but I'm going to go ahead and do this to kind of show you what's happening here. See, so what happens is this cube root chews up all of these cubes. So the cube root of y to the third is y, y, y. So those three come out, and this cube root of 8 out here comes out as 2. Okay, so I'll go ahead and underline that. So the final answer, when you simplify this, you're trying to get all of those perfect cube numbers out from underneath the cube root, and you're going to get 2y cubed, and what's left? The cube root of 5y. So this and this is trapped under the radical. They're probably going, hey, these guys that broke out, take us with you, but they're trapped because there's only one of each one, and they can't get beyond this prison guard of 3 here. And you notice there is no cube root number up here that 5 goes into, that breaks 5 apart. With the first cube root number besides 1 is already past 5, so we're done. All right, let's try a couple more here, and we will move on to the next section. Now, I'm going to take another square root problem here. How about the square root of 24 a to the 6th power, b to the 7th power. Okay, now if you want friendly square root numbers that go into 24, let's just go down here. Here's how you get friendly square root numbers. Now 1 never helps us, so I don't know why we put 1, but I will just to show it. 1 squared, 2 squared, 3 squared, 4 squared. And I already see one of these is going to help us simplify the square root of 24. So we're going to use the product rule and break this apart into the square root of 4 times the square root of 6. The square root of a to the 6th power I'm going to leave alone since 2 goes into 6 there evenly. So you're looking for these root numbers that go into the power. And on the b to the 7th, see, I'm going to break that up into the square root of b to the 6th times the square root of b. Since, again, 2 goes into the 6. All right, now let's have coming out of the Radican party, as I like to say. So what's coming out of here? I'll underline them in pretty purple. We're going to have the square root of 4 simplifies the 2. The square root of a to the 6th power, a to the 3rd, using that e over r rule there. B to the 3rd, and what doesn't make it, left it in the radical, is the square root of 6b. So I hope as we do enough of these examples that you will see what we're trying to do. We're trying to, on square roots, get all the perfect square numbers out from underneath the radical. On cube roots, we're trying to get all the cube roots out from underneath the radical, and so forth and so on. All right, now I want to do a few more with fractions because I know y'all love fractions and so forth. So here comes the quotient rule one more time at you. The cube root of 10 divided by the cube root of 2, directions say use the quotient rule to divide, is simply the cube root of 5, 10 divided by 2. Now you could have also taken those 2 little radicals and made one giant radical out of them if you wanted to. So that quotient rule says that you can make one giant radical or itsy bitsy radicals. All right, let's try another one. The square root, and I'm trying to mixing up square roots and cube roots and so forth, just to keep you honest here, of a7 b6 over the square root of a cubed b squared. Now, whenever you divide same bases, this is good exam review, subtract the exponent, see? So what you're going to do is just like we did back in Chapter 5 when we were doing sections 5.1 and 5.2, a7 divided by a3, a to the fourth power, and also we would get b to the fourth power, b6 divided by b2, subtract the exponents. Now looky here, two nice perfect square numbers, 2 goes into 4, and here comes your final answer. All the A's and all the B's did a jailbreak there and came out from underneath the radical, and that's it. All right, let me try one more here, and I'll go back to a cube root. Let me clear the slide. I'm going to take the cube root of 128 x cubed divided by -3 times the cube root of 2x. Now again, the quotient rule says we can divide cube root by cube root, and 2 goes into 128 64 times, and the x cubed divided by the x here would leave us with x squared. So the 2 cube roots simplify to this using the quotient rule, but don't forget, we have a number on the denominator that we can't lose sight of. It's still there on the outside of this radical, so be careful. Now, cube root of 64, let's run through those cube root numbers real quickly to see if we can simplify this. 2 cubed is 8. 3 cubed is 27. 4 cubed, that's a bad cube though. Let me make that 3 cubed a little better there. Okay, is, oh, look at that, a friendly cube root number. So the cube root of 64 will simplify to 4 times the cube root of x squared all over -3. So this one, the cube root of x squared did not escape the radicand because it did not have enough on the powers to do so. All right, now there's one other thing I want to talk about here, and I'm going to pull up a piece of graph paper. We haven't graphed anything in a long time, and maybe we can go ahead